Great. Yeah.
Thank you. We have 40 minutes, Professor. Thank you.
Okay, thanks. Yeah, no problem at all. Good morning, everyone. Today, I would like to talk about next generation Internet of Things and how to use it to build new smart systems such as cyber-physical system. About myself, my name is Xiaodong, and I came from Edinburgh Napier University in Britain. And you can see my email and welcome to contact me for possible research collaborations. Oh dear. In Edinburgh Napier, I'm leading a research group. Its name is IntelligenceDriven IoT and Smart Systems. Our current research focus, I show it in this slide. Basically, we are focusing on developing the so-called smart pervasive system, particularly the IoT-based smart systems. Of course, we use AI technology to drive this kind of system. Cyber-physical system is one, probably most important example of this kind of smart systems. When we say we are using AI technology, basically we mean, firstly, we are using deep learning, machine learning technology, which is very common now. And meanwhile, we are using so-called knowledge-based technology, such as knowledge engineering, knowledge base, inference, and we are trying to link the two parts together to make the AI working. The first step is to make the data understandable by the machines, by the computer. So we are working to develop semantic data models for the data in this kind of smart system and for the data analysis of in this kind of cyber-physical system. Cyber-physical system is an interdisciplinary research area. To make it successful, you not only need data, not only need AI, you need software engineering technology, how to design the architecture for this kind of system, how to accommodate the AI components, how to accommodate the data analytic components. So we are researching the latest software architecture for cyber-physical systems. Notably, microservice-oriented architecture is the first choice for us. The cyber-physical system, to support its running, usually people deploy it in the three-layered environment. That's the cloud, edge, and IoT devices. How to coordinate to make these three layers working seamlessly, cooperatively. So cloud edge IoT continuum is another research area we are interested in. The software, the whole system of a cyber-physical system keep evolving. So software evolution is another research focus from us. Overall, I would say our research aim is to develop the new approaches, models, and architectures to improve the engineering of these so-called emerging software-driven systems. Any new features for these new systems and the new functionality and new structure. All these are our focus. So we may define the same we are doing as intelligence-driven system engineering or software engineering. The relationship between IoT, internet, and smart system, we can describe it in such a diagram. IoT definitely is the core foundation for any smart system, including cyber-physical system. We need the IoT technology. Of course, IoT is based on future internet technology, but the concept and the technology for smart system is wider than IoT itself. Not only the sensors, not only the Wi-Fi network, not only how they communicate, we also need to include the system architecture, wider hardware, and wider system features. For the next generation IoT, the challenges we are facing, the first one is it indeed is a multiple disciplinary research area. To build the next generation IoT, we need the concepts and techniques not only from computing, not only from even engineering. We need techniques from so-called non-technical or even people say the social disciplines, such as we need psychology, we need cognition science, we need human-machine interaction, the interaction design, because this part, they are going to handle how the system will interact with the human users, how to make the whole system human-centric and even further beyond. Technically, we need system architecture for the IoT, for the IoT-based system. We need so-called system intelligence. By system intelligence, we mean AI technology mainly. And this AI technology not only including the latest, most popular machine learning, deep learning technique, and it should include the more traditional knowledge engineering technology. The two parts should both be included and should work collaboratively. The communication is a key part, of course. So 5G, 6G technology, that's something we need to consider when building the next generation IoT. Of course, security and privacy is a very critical requirement for the IoT and for the next generation IoT. The desired features for the next generation IoT, they are quite challenging. Firstly, we would say the next generation IoT must be more human-centric. It must understand human need, human context autonomously, and must be able to make a response around these kind of human needs. So we say the whole system must be more human-centric. The whole system must be open. It must be an open system. Means everyone, every system in the world should be able to join, should be able to contribute to the domain, to the technologies in this domain, and to an existing system. The new generation IoT will support collaboration across the border technically, across the border of departments, and across the border of regions. It's a decentralized system and it must be more inclusive, means inclusive for people, for society. It must be able to protect the privacy and The whole system must be able to run autonomously, and meanwhile, it must be able to win the user trust. People talk about explainable AI. Yeah, that's one aspect of this trust words. Okay, so it must be autonomous, must be intelligent, and meanwhile, it must be trustworthy. To make these challenging features of next generation IoT happen, we need a lot of enabling technologies. And these technologies must be engaged seamlessly and integrally. What techniques will need? My observation is we will need the 5G, 6G network, that's for communication, and we will need AI technique, that's including machine learning, deep learning, and also include knowledge engineering, and include how to link the two parts together to make the intelligence, to make the machine learning explainable. The whole architecture, particularly the software architecture for the next generation IoT and IoT-based system, must be dynamically adaptive, means it can be adapted at runtime autonomously. That's an important feature people are desiring. Okay, and microservice could be a good solution. And we need a technique about cloud, edge, fog, and IoT itself, and their continuum. Yeah, digital media and human-machine interaction, that's something we definitely need. We want to make the interaction more natural for human being. Okay, so technique and interaction design theory, that's a must. To make the IoT-based system more secure, one technique we can use, and one technique which is very matching with the features of IoT, I would say that's the blockchain technology, because blockchain is a distributed blockchain can have numerous nodes. Okay, so it's a very ideal choice. To conclude, I would say next generation IoT will be software defined. Yeah, software will play a very critical and very wide role in the next generation IoT. And in the modern IoT, we will need the co-design of both hardware and software and the network. Why? Because the IoT of the next generation will be so complex and will have very high intelligence. So only if we can engage hardware, software, network seamlessly in a co-design manner, then the challenging features of the IoT will be able to be achieved. In the second part of my talk, I would like to talk about technology we developed as an example of the next generation IoT and as example of the effort to develop new types of cyber-physical system. The name of the technology is context active resilience in cyber-physical system. Yeah, the project was sponsored by the Horizon 2020 Marie Curie scheme. Okay. What is cyber-physical system? I think all of us understand this. very sharply now. Basically, you can understand a cyber-physical system as a modern, comprehensive control system. It has a feedback loop. So the real world inside it, we are going to deploy many smart sensors and many actuators. And the sensors will get the will sense the signal, sense the state of the physical world. And this step is physical sensing. And with this physical sensing, the sensor signals will be sent to the computing world, cyberspace. Cyberspace, of course, you may have edge, you may have cloud, and you use AI, you use software engineering, basically to make the computing software running. And the decision and analysis will happen in the cyberspace, and the decision and actions will be sent to the real world as actuation information. And this kind of actuation information will drive the motor, the devices in the physical world. And then the physical world, its state, its structure will change. Cyber-physical systems have been applied to the society, to the economy, to our daily life so widely. So there are millions of examples. We got smart energy. Yeah, we got smart city, smart building, smart home, and we got smart traffic, smart transportation. We got smart manufacture, industry 4.0. Yeah, we got smart healthcare. So numerous examples. The cyber-physical system, they playing very critical role in the society, in the economy. So one paramount requirement for cyber-physical system is highly resilient. Yeah, the system must be fault tolerant. If any hardware go wrong and any software going wrong, or even further, the system is subject to some malicious attack from the hacker from anywhere, then the system should be able to recover from this kind of faults and attacks and should be able to maintain the acceptable level of operations as much as possible. This feature, we define it as resiliency. Although resiliency is so much desired for modern cyber-physical system, the current state of art is the resiliency technology mostly they are responsive or they are quite passive only. So they didn't, you know, dynamically adapt the whole system in an active manner to support the resiliency in a more active mode. You know, inside a cyber-physical system, there will be many human users. There will also be many hardware components and software modules. Each of these can be considered as a key component in the cyber-physical system, and they will have the need, the profile, and their intention. All this, we can model them as so-called context. So we advocate a modern, the future cyber-physical system should be resilient in a context-active manner, and the resiliency should be context-active. In this project, The methodology we adopted is use case-driven agile spiral methodology. The use case will play a key role, and is you can see in the methodology we have 2 cycles. In cycle 1, yeah, we have a use case work package. So we take a smart home as a use case, and from this smart home use case, we detect the requirement for the new cyber-physical system. And these requirements will be feedback into the technology work packages, that's work package 2 and 3, which will focus on developing approaches, patterns, and intelligence of the system. And this kind of technologies and models we developed will be deployed in the use case of the smart home. Okay, then we got the first prototype. Then we will be able to move to the second cycle. The initial version of the prototype of smart home will be evaluated by the user, and again we get feedback and we get observations and requirements about how to improve this kind of smart home. And then based on this, we are going to expand and refine the approach pattern and the intelligence in work package 2 and 3. And then the new models, new approach will be used to develop the second version of the prototype. We used the IoT Lab. We give it the name Sensorium Lab. So it has lots of sensors. It can be treated as a smart home environment or smart office environment. And it has the, the software for emotion detection, emotion analysis. So all this kind of, let's say, IoT technology. The whole project includes 5 work packages. Work package 1 is a standard project management. Work package 5 is also quite standard. That's dissemination and exploitation. The technical work package include work package 2, context active resilience mechanism, and work package 3, context active resilience patterns, and work package 4, the use case of the smart home. I won't go to the very deep technical details of this project, but I would like to present some key profile of this technology as an example of how the system is developed and how it works. For the context model, we used ontology technique, and the context model we got include 4 layers. Yeah. As shown in this diagram, that's the yellow, orange, blue, and purple 4 parts. Each part is a layer. The most physical layer is showing as yellow. That's the sensor layer. So the sensor will detect the signals from the physical world. And then the physical sensor signal will be sent to the second layer and being converted into machine understandable data. That's the orange color, that layer. As example, in the sensor layer, we may detect GPS coordinates, which is a physical signal. And this, in the data layer, will be mapped to more meaningful semantics. such as we know the location means a dining room. We know the location meaning a sitting room or meaning a kitchen. The third upper layer is blue layer. That's the context layer. So we are going to analyze the data in the data layer and going to detect the context. Example of context could be we find out the user is a senior citizen and he is in the bathroom or he is in the kitchen. So that's the context and what they need. All these are context. The most top layer is showing in purple. That's the activity layer. Basically, it means we are not only going to know, the context, but also we are going to detect some activities about the hardware component, about the human user, such as we detected the senior citizen is in the sitting room watching television, want to calm down, okay, from some quite emotional matters. The context active resilience framework, it works in 4 parts. From the physical space, we got sensors and it will detect the context and it will get the signal, convert it to data and get some very basic context here. And the context is saving in the context database represented and some basic reasoning happening in the physical space part. And then we are going to move to the activity mapping part. We use the deep learning technique, probability model to detect the activities. Okay, that's activity recognition. And we predicted the activity, you know, in the next step. Okay, that's activity prediction. Based on the activity we detected and predicted, the system intelligently pick up so-called proactive adaptation patterns, from the repository. And these proactive adaptation patterns will then be applied to the physical system, the environmental mapping part. And by applying these adaptation services, the interface of the cyber-physical system can be adapted to the user's need, and the function can be adapted, and the quality of features can be adapted. Okay, that's the technical part of this, say, a car technology. We beyond the technical development itself, we actively engaged, entered public engagement. We actively uh, we actively engaged in the industry dissemination and exploitation. We contacted many institutions, public organizations, did the road show, did the industry showcase, and we contacted quite several companies, trying to commercialize the technology we developed. Okay, I think that's nearly 40 minutes now. So that's all I prepared to present to the conference. So I'm happy to take some questions. Yeah, we still got a few minutes. Okay, thank you for your interest.
Thank you so much, Professor Xiaodong Liu. Your presentation was extremely interesting and motivated. Dear colleagues, we have time for your questions. Any questions? Okay, I have one maybe more philosophical questions. In the beginning of your presentation, in your contents, you thought about continuum,
Yes.
edge, IoT, edge, and cloud. We know that there are fog and other levels of these continuums. What is your opinion? How much such levels will be in future? Now we have discrete hierarchy, yes, 3 or 4 levels. But step by step, we can go ahead, and the number of levels can be increased. And the question is, what your opinion concerning future of this hierarchy in context of your presentation? I mean, security issues for such kind of infrastructure, IoT-based systems. Thank you.
Yeah, the continuum is a very complex issue. Yeah, we got Fox, and we currently, okay, let's say we got 3 layers in the continuum, and because the whole system will be deployed across these 3 layers, and yeah, all these are networked, so security privacy will indeed be a critical issue. So my view is blockchain is a very good choice for IoT-based applications. Yeah, particularly at the IoT layer, you got many sensors and other devices. So each of these may be considered as an agent and may be considered as a node in the blockchain. And then you design a protocol, such as for the digital identity identification, and so the whole blockchain, can run in a peer-to-peer structure, and to make it more efficient, again, we need to put much blockchain related computing at the edge server, and even further we put some at the cloud layer. But the higher we put something at the layer, then it will become less real-time real-timely responsive. So real-time, response is another challenge. So when we deploy the services and also the blockchain security services across the 3 layers, then we need to consider the real-time response. So something, we may deploy it at the IoT layer, which can be very much real-time, but the computation power will be very limited at the IoT layer. And then edge layer is in the middle, and then cloud layer, that's usually give you quite long delay in the response, but it can be a background layer to do some background non-real-time work. Okay, that's the idea I got in my mind at this moment.
And thank you so much. As I understand, now we have metrics with hierarchy level and horizontal ones, and these metrics should be resilient. And any new vertical or horizontal entities should not not should increase it risks of successful attacks. Hence, I think it's very interesting and very challengeable task. Thank you very much. Dear colleagues, who would like to ask Professor CyberPhysical?
Yeah.
Yeah, we see. And Professor Tatiana Shmylova.
Oh.
Thank you. I am from National Aviation University, and I have a question about human factor. Influence of human factor in your system. And the first, resistance from operators error. And did you have statistical data about influence of human factor on your system? But for example, in aviation, 17% of human factor in all accidents in aviation. But about your system, level of diagnostic of error of human, only human factor, influence of human factor on your system in job. Thank you.
Yeah, that's a very interesting question. The human factor in the system we considered, I would say perhaps that's 40%, something like that. Yep. And we focused on the yield current, that part. Yep. So what they need and how they can be more socially inclusive, such as if the senior citizen feel lonely, yeah, because of COVID isolation, and then how the system may suggest some services, may provide some activities to, make the user or the senior citizen feel more inclusive. That's I would say that's the human factors they considered in the system.
Understood. Human factor, this is important in the different job, in different wagon, because this is a operator, this is a human, and it's life. But your system very important in job. But the first from human, the first from operators in job, this is important. Thank you.
Yes, definitely. Yeah, I think that's something we need to further enhance in our future research work. Yeah, so myself and including my group, we know some concepts of human-centric, but overall, we are not expert on that part. So we do need, to explore more in that part and perhaps, collaborate with some experts in that part. Yeah, in the future research.
No, yes, thank you. Interesting.
Yeah.
Thank you. Any other questions? I don't see, and in our chat, no. Dear Professor CyberPhysical, thank you very much one more for your very interesting presentation, for our discussion, and hope we will continue our cooperation not only in the DESSERT community, the DESSERT conference, and in maybe